to invite our next speaker up to present on computing probabilistic bisimilarity distances via policy iteration. This is
Thank you. So it's joint work with my graduate student, Chi Tan. So the talk will be in two parts. First, I'll talk about models, and in the second part, I will talk about algorithms. It is related to the previous talk, and you'll see a number of notions popping up that we've seen before. The overall talk is related to this fundamental question. So when do two states of a particular model behave the same? And for this, we usually use behavioral equivalences. I mean, many have been introduced over the last 30 years. So we're looking at these equivalence relations, in particular for a model that we're interested in, which are labeled Markov chains. So these are normal Markov chains. So you have a bunch of states, and you have probabilities going from one state to another. And we label the states, and the labeling is done in this example, by coloring the states. And it captures properties that hold in those particular states. So for example, these three states have the same properties, and these two have different properties from those other ones. And so the transitions, which will play a key role, I will model by a function. So it's a function from the set of states. I assume this set to be finite, to distributions on this set. So if we look, for example, at this one over here, tau of S will be a distribution on S, and it maps to the state U a half, to the state V a half, and to all other states 0. So we'll use this later on. So now the notion of equivalence for these type of systems was introduced by Larson and Skaw, and it's known as probabilistic bisimulation. So a relation on the states is called a probabilistic bisimulation. First of all, if related states satisfy the same properties. So that means that their labels are the same. And furthermore, there's some dynamics. So you're in these two states, and then you make a transition. But remember, the transition function takes a state to a distribution on states. So what we get is we have this pair now of distributions, and we want to see that they are related in some way as well. So what we have to do is we have to take a relation on states of the system to a relation on distribution over those states. So we have to lift this notion of relation, which I'll do in a minute. So once we have this notion, then probabilistic bisimilarity will be the largest such equivalence relation. So how can you do the lifting? So this is one way. So you take an equivalence relation, and now you lift it to a relation on distributions. And so two measures or two probability distributions are related if they assign the same probability mass to equivalence classes. So the idea more or less is that, so when are two states the same, if they satisfy the same properties, and also if you make a transition, then you go with the same probability to equivalence classes of states again. So next what I will do is I'll provide an alternative characterization of this notion of lifting, which I will use later on as well. So key ingredient of this alternative characterization is the notion of coupling. So given two probability distributions, then a coupling is again a probability distribution, but this time on the product space, such that mu and nu are the marginals. And that is captured by these two equations. And this will be the notation that I will be using for the set of all the couplings. So it might be helpful to actually look at an example to see how this notion of coupling works. So what we could have is the following situation. Again, you can think of this as states and transitions, but you can also think of this as a probability distribution. So the probability of being here is a half, and the probability of being here is a half as well, and the similar on this side. So we have now mu and nu. Another way to actually view this is to think of this as a transportation problem. So we have a bunch of stuff, let's say 1 unit of stuff, which is over here. Half is transported over here, half is transported over here. And now what we want to do is we want to transport it from this probability distribution to this one over here. And so how much do we want over here? A half. And how much do we want over here? A half. And now the way to transport this, these are actually the couplings. Again, the coupling, what does it do? It maps every pair of probability. That's the amount of mass that we're going to transport from one state to another. So for example, one way to do this is to transport it in this way, right? So we're just transporting a half over here and a half over here. But of course, you could also cross. For example, there will be another example of a coupling or a transportation or a flow. So the alternative characterization now in terms of these couplings of this notion of lifting is the following. So again, we have two distributions, and they're in the lifting if and only if we can find a coupling such that the support of this coupling is a subset of the equivalence relation. So now there are infinitely many couplings. There are infinitely many ways in order to transport information from the one side or other stuff from one side to the other. For example, we can pick any r in this interval over here and then transport this and then transport that. So once you choose the r, then of course you get the other transportation part as well.
Franck, shouldn't you have one there, 1 minus r, not 1 half minus r? Shouldn't be 1 there?
I only have a half here to transport, right? So the maximum I can transport from here will be a half, right? So
and the
that's
overall sum wants to be 1 as well. So that's... Yeah.
Thank you. So there are infinitely many. However, I mean, this set of couplings is a convex polytope. And a property that we'll use in a bit is that a concave function on such a polytope attains its minimum at a vertex. And the set of vertices, which I will use with this V over here to denote, is actually a finite set. So, and in this particular case, there are only two vertices. So only when you choose r to be 0 or a half. So these are more or less the extremal ones that you can have. And what one can show is that, again, for the lifting, you only have to show that there exists a vertex that has this property as before. So you can actually restrict to the vertices rather than looking at the complete polytope. And just to give you an idea of roughly how to prove this, so what you could do is you could take all the states of the set S and you order them in such a way that related states, related according to the equivalence relation R, are next to each other. So once you've done that, you can run the northwest corner method, which is, for example, used for linear programming. And this is now you get a really simple algorithm with a bunch of loops and some nested loops as well. And now actually proving this result really boils down to proving a bunch of loop invariants. So initially I tried to do this by hand and failed miserably because I would make all kind of silly small mistakes. So recently we've been using this tool, Daphne, which allows you actually to annotate this simple program with loop invariants, and it actually proves it all automatically.
Question?
Yeah.
So can you explain in your previous example what is R bar? Is it a set of all 4 possible transitions, or?
What is R bar? That's the R bar. So R is a relation on the states, and now you want to lift it to a relation on the measures. I think I'll have an example later on, which I'll come to soon. If you a bit of patience, and if I don't answer your question, feel free to interrupt me again, and I'll try it again. All right, so we have this notion of behavioral equivalence for these systems, but it's well known that this notion is not very robust. And what does it mean is that if you have two states that are considered to be equivalent, if you change the probabilities just slightly, they might become inequivalent, or vice versa. And since we generally get these numbers just by running some experiments, or possibly even by guessing, I mean, it is it's tricky to use this very strict Boolean type of notion. And therefore, others have suggested to use, instead of a behavioral equivalence, to use something which is called a pseudometric. So rather than saying yes or no, they behave exactly the same, what we do is we give a kind of a quantitative measure of how similar the behavior is of the states. And the idea is that the smaller the distance between two states, the more alike they behave. And if the distance is 0, then they behave exactly the same. So going back now to probabilistic bisimilarity, a little bit more interesting example here. Again, we have a distribution here and here, and this is the condition that we have to satisfy in order to do the lifting. So now, indeed, let's come up with a relation. So the green edges capture which states are related. And now what we want to do is we want to find a way to transport the such that we're only using the green edges, right? And so we can do this, right? So for example, a third over here, a third over here, these are connected, and 1/3 over here, and these are connected as well. Right? So this now shows that if you have R, the relation, and you have a measure over here and a measure over here, then these two measures are in the lifting of R, because this condition is satisfied. All right. So now, in order to move towards from this Boolean notion to something more quantitative, what I'll do is I'll first start with taking this relation and already more or less describing it as a distance-like function. So we say that if two states are related, we map it to 0, otherwise we map it to 1. And we had this condition that the support of the coupling should be a subset of R. So now you can rewrite this in the following way, right? So you can say that this weighted sum has to be 0. So now the next step, what we're going to do is we're going to take this relation and map it into a pseudometric. So it's not going to be 0, 1, but here we're going to get arbitrary real numbers in the unit interval. And so, of course, at that point, we cannot really insist on this being 0 anymore. But what we can try to do is we can try to minimize this. So in a sense, what we're trying to do is find the coupling that minimizes this sum, where this is now going to be a real valued function rather than a discrete function. So in this setting, we're more or less allowing, to transport anywhere we like. But remember that we've replaced the relation with a distance function. So there's a cost associated with moving into between different states. And now what we try to do is we try to minimize, try to find an optimal coupling that minimizes this weighted sum. That's all?
Is it like a conservative extension? Can you take a metric that's like 1 on the support of R and infinite outside or something? And when you minimize it, you're solving the preceding problem?
So probabilistic bisimilarity exactly if and only if distances are 0 in this particular setting. So in that sense, it gives you the extension.
No, I meant differently. I mean, can I embed the exact... So I pick a particular D and I apply a minimizing objective. Yeah. And my D is somehow I put the points that are in the support of R at distance 1 or something, and the ones that are not connected are at distance infinite. If I minimize that, will I find the same concept as before?
Yes. Yes.
So, it is the same as the Earth mover's distance?
Yes, it is. Yes. Yes, go ahead.
So this notion of similarity seems to be, it's like a single-step notion of similarity. Whereas,
yes.
So is there a notion which, say, pays attention to where things lead to further on in time? Because, for example, there could be some small transition to a different state. Maybe it doesn't cause, I don't quite understand this yet, but maybe it doesn't cause the distance to look too bad, but then that state could lead to something very bad down the road, and then would that be reflected in a measure like this or not?
It is somewhat reflected in it, and we'll see that later on, because actually the distance function itself is defined as a fixed point. So you will see changes in the future as well. So here we're looking at indeed at the one step, but then once I introduce the distance function itself, you'll see that it is defined recursively. So it will capture that. There are also many other distances that have been introduced for these type of systems that are defined in different ways and more along the lines that you would suggest. So this was the definition of probabilistic bisimilarity, right? The largest equivalence relation, labels are the same, and we have to be able to find a coupling that has this property. So now if we want to generalize this, what we would get is the following. So we now get the smallest distance function, and smallest because we decided that 0 matches true in some sense. And so therefore 1 is false. So obviously if the labels are different, we want them to be maximally different because you want to more or less flip this idea over here. And then the existential quantifier becomes a minimum, and as we already discussed before, this over here becomes this weighted sum. So this was the distance function that was introduced in the late 90s by Desana, Gupta, Ajita, and Panagadan, and one of the fundamental results that they proved in their paper is that probabilistic bisimilarity exactly coincides with states having distance 0. So this is indeed closely related to the Earth moving distance. It has many, many other names, including the Kantorovich metric. So this is the definition that we more or less recognize from one of the previous slides. And as I said, concave functions take their minimum at a vertex. So really, that's why these two equations are the same. This is concave, and so we can focus on the vertices. And then this one over here is a duality theorem due to Kantorovich and Rubinstein. And this is what you usually find as the definition of the Kantorovich metric. So in the second part of the talk, about 20 minutes, I guess. I'll present some algorithms in order to approximate and compute these distance functions. And I'll quickly show 3 algorithms, and then I'll focus in on one of them. And then we'll come back to games, as we've seen in the previous talk. And hopefully I'll have time for the last part as well, and otherwise we'll skip over it. So how can we compute these distances now that we've defined them? So the first approach that we took was using the theory over the reals. So what you can do is you can express this over here. So the distance between S and T is smaller than some rational Q. You can express this in the first order theory over the reals. And then you just use binary search, right? So you first check, is the distance smaller than a half? If it is it smaller than a quarter? If not, is it smaller than 3/8, and so on. And so in this way, you approximate it. So at least that showed that you can compute these distances, but not very efficiently. So after that, we were trying to find out a better way to do this, and it turns out that you can actually express the distance between two states as one big linear programming problem, which you can then solve using the ellipsoid method. And for those familiar with the method, you need a separation oracle. And in this case, you have to solve some sort of minimum cost flow problem, and that you can use the network simplex algorithm, and you can do this in polynomial time. Yes.
How big is the linear program?
Sorry?
How big is it, the linear program?
How big is the linear program? It's a polynomial size of the system. So it does give rise to a polynomial time algorithm. And the third algorithm was introduced by Bacci, Larsen, and Amadare, and they use some different techniques related to some of the ingredients that I've presented to you at the first part. The algorithm itself consists of a basic algorithm, and I'll focus on that only in this talk, plus some optimization. And the idea is that you try to compute distances on the fly. So you're not computing all of them, but only those that you really need. But I will not focus on this, although all the results that I present actually carry over to the full algorithm. So it is all based, on simple stochastic games. So let me quickly introduce those. They're simpler than the one that Marta presented to us. So it's a directed graph. You have a bunch of different nodes. So you have min nodes, max nodes, average nodes, and you have two sinks, a zero sink and a one sink. And there are two players. There's a min player and a max player. So if you're on a min node, the min player plays, and the max node, the max player plays. If you're on an average node, with 50%, you go over here, and with 50%, you go over here. So what are the objectives? The max player tries to maximize the probability of reaching the one sink. And the min player obviously tries to either avoid ever reaching this one, or it tries to reach the zero sink. And so now you can assign to every node of the graph a value, which is more or less the probability that the max player will win. So for example, if you're in this node, then there's no way that the max player can win, because you always go to 0, right? So this would have value 0. This one will have value 1/2. This will have value 1/2. And this will have value 1/2 plus something more, right? Possibly, because that's going over here. So now again, what would be a good strategy for the max player? If I'm over here, this is 0, this is 1/2, so the strategy would be to go over here, right? And here, the strategy would be 1/2 or something 1/2 plus something more, so the strategy would be to go over here. And finally, here the min player has to choose between 1/2 or 1/2 plus something more, so it will probably, it will choose this strategy over there. So as I already mentioned, the value of a vertex is the probability that the max player will win the game, provided that both play optimal. So now what we can do is we can take a labeled Markov chain and we can map it to a simple stochastic game in such a way that the distance between the states, so actually, by the way, I should mention that you map every pair of states in the labeled Markov chain to a vertex of the game, such that the distance between every pair of states is exactly the value of the vertex. And furthermore, there's an algorithm called simply policy iteration, which exactly now boils down to the algorithm that was introduced by Bacci et al. So how do you do this? So you take a pair of states of the labeled Markov chain. If the labels are different, well, then we know that the distance is 1. They behave very differently, so you map it to the one sink. If they are probabilistic bisimilar, then we know that the distance is 0. They behave exactly the same, so we map it to the 0 sink. And otherwise, what do we do? So we have a pair of states S and T. So we have an edge to all the vertices. And now, of course, here it's essential to use vertices so that we get a finite set. And then this has to be a min node, so we're minimizing over all the vertices. And then these are our average nodes. So that's why we get this sum over here. Since this is an average node, you have to associate with it a probability. Remember that this is a coupling, so it assigns to every pair of states a probability, and that's exactly the probability of this edge over here. Right? So this maps now a labeled Markov chain to a simple stochastic game. And then simple policy iteration allows you to compute the values. And so what do? You choose an initial policy. Also, Marta mentioned the word strategy, which is also often used. And as long as there's a particular vertex in the game that is not locally optimal, then what you do is you switch it to an optimal one. So you adjust it locally, and you keep doing this until everything is locally optimal. And then there's the Condon showed that if the game terminates with probability 1, then it actually computes the global optimum as well. I think I'm going to skip this part. All right. So one of the things that we've done is we've shown that the algorithm is exponential. And so I'll give you a And again, I mean, the obvious way is to implement an n-bit counter in order to show this. So let me show you a simple example. So this is the counter example. So this is a labeled Markov chain. And so what we do is we take this labeled Markov chain and then first we build a game from it. And the game looks like this. These over here are all min nodes, and the dots over here are the average nodes. And as you can see, it doesn't include any max nodes in this particular counter example. So what we do first is we have to choose a strategy, which means that the min player has to choose which option to choose. And as you can see, we're only interested in 1, 2, 3 of these nodes, because here we have two options. We can either go down or we can go to the right. So let's say that we start with this particular initial strategy. And then what we can do is we can compute the value right now. So this one is 1, right? Because it's the average of 1 and 1. And this one is 1 as well. And of course, that one is 1 as well. We can also compute the values of these over here. So this one is 1/2, and this one is 7/8. Now you can see that this one is locally not optimal, right? Because if I switch, it will become smaller. Right, and we're trying to minimize this. So what we'll do is we'll switch this one over here, and as you can see, the value becomes smaller, so that's good. So that's our first step. And now we can see actually that we could switch this one as well, because it becomes smaller as well. But now we can switch the first one back again, because it will become smaller as well. And so I hope you see that there's this counter going on. So then we switch this one. Then we can switch this one again, and we can switch this one. So I think we had now all 8. I mean, so let's see. Okay, so the first one is 1, 2, 3, 4. All right. So we also did. We implemented the 3 algorithms as well, and did some comparison of the performance. We used a simple example of a particular algorithm, and then modeled it as a labeled Markov chain, and then ran the 3 algorithms. So if you do the one with the first theory of the reals, I mean, it really goes nowhere. I mean, it's just simply too big. I mean, the formula becomes huge, and if you run the algorithm, it's not going anywhere. So for the second one, the best I can tell you is that it takes more than 10 hours, because my grad students sent me an email this morning. I mean, they're 3 hours ahead, and she said, it's still running. So I can't tell you exactly the amount, but at least 10 hours. Now, the third algorithm, which, as we've seen in the worst case, is exponential, is extremely efficient. And you can see 10 hours versus a couple of seconds. Also, what you can do is you can actually pre-process and first, more or less, compute which states are probabilistic bisimilar, and then we'll run the algorithm. And it turns out that actually this gives a speed up. All right. So what we've seen is that the algorithm that was introduced by Bacci et al. is really simple policy iteration. And one of the key things that we observed is that you need to decide probabilistic bisimilarity before you actually compute the distances. And this is not actually the only example where we've seen that although we're interested in a much more refined and continuous notion of equivalence, first deciding this more discrete notion really helps. I mean, for example, for the ellipsoid algorithm, you can prove that if you first decide probabilistic bisimilarity, then the problem becomes fully dimensional, and then you get a more efficient ellipsoid algorithm as well. I mean, still not very efficient, but it does help.
But is it robust? Because to do this first, is it continuous to your imperfect notion of exact bisimulation?
What do you mean exactly?
All right, maybe I'll ask again at the end of the talk.
All right. Shown a simple example that it actually takes exponential time, but in practice it works really, really well. So we've been doing some related work. So we're also interested in this notion of general policy iteration. So the key difference between simple and general policy iteration is that in simple policy iteration, in the loop, you update a single vertex in every iteration that is locally non-optimal, and then you recompute everything. Whereas in general policy iteration, you try to, you switch all the vertices that are locally non-optimal, and then you recompute all the. And it seems that this might actually be more efficient. And furthermore, what we've done is we've applied at least, we've done already simple policy iteration for models that can also express not only probabilistic notions, but also non-deterministic notions, so probabilistic automata. We've done it for simple policy iteration. Turns out that in that particular case, you not only have to decide first the states that have distance 0, that is, are probabilistic bisimilar, but you also have to decide the states that have distance 1, that are the most apart. But that can be done in polynomial time. We're still looking to see if we can extend this to the general policy iteration setting as well. That concludes my talk. Thank you for your attention.
So n here is the number of states, is that right? And we talked about the complexity of, you said it was, let n be the number of states.
Sure.
So I imagine in many applications, n is exponential in already in some natural parameters, right? And then probably, so even doing a single passive policy iteration is too expensive. So is there work that looks at, say, approximately computing the distance up to some error with high probability, and say doesn't necessarily even investigate all the possible states? Or,
yes.
Yeah,
So people have been using sampling in order to do this.
And so from your perspective, are those? Is there some reason? Are you working in some setting where the guarantees provided by the sampling algorithms are just not cut it for some application? Or maybe in practice, like are these methods competitive with ones that are doing, say, much more, making a much greater approximation?
So they're definitely not competitive with the sampling algorithms at this time.
Yeah. But what criticism would you levy against the sampling, if any?
The guarantees that they provide. Here we exactly compute the distances, whereas otherwise you can recode it.
Yeah.
I think I have a very similar, I mean, not exactly the same question, but something similar. So all this is predicated on the premise of having a robust, some notion of equivalence or nearness, which is robust in the setting. And it can be that we don't know the probabilities very well, or it can be that maybe we have a reduced coarse-grained version of a system which is too large to run that type of algorithm on. So for the first question, do you actually prove that your bisimulation metric is continuous with respect to some kind of topology on the, let's say in the finite case in a set of weights of your kernel, the one you start from?
Yeah, so the idea is that, for example, if you take a system and you modify one of the probabilities continuously, will your distance function be continuous as well? And that's the case.
So do we have? Can we say a little more? Can we have a Lipschitz bound or something? Do we know?
Again, I mean, so there are some Lipschitz bounds, for example, when you want to compose systems, right? So if you use operators from process algebra and you take these systems and you combine them, then you again, the idea of in a Boolean setting, what you would like is that the behavioral equivalence is a congruence, right? And in this particular setting, what you would like is that the operators are non-expansive with respect to the distance function, which they are.
I mean, around 0 would be funny, right? You turn something from 0 probability on, And then relates to my question about what if you go from zero probability to some really aberrant state to positive probability, and now something that was impossible is now possible in the long run. That would seem to. I mean, maybe it would still be continuous, but I would be surprised if you could put some kind of Lipschitz bound on it or something.
Still in the same vein, how does it behave with respect to averaging probabilistic systems? So, we have this theory of approximation for averaging if you're given an ambient probability. Do we know something about how the bisimilarity metric behave under this kind of transformation?
I wouldn't know.
Or other notion of approximants, maybe?
I think Jose has some results in that direction.
This is for probabilistic automata only, right? There is no non-determinism, or does it work, or the algorithm works also for when you have non-determinism in addition to probability?
Okay, so in the case that we move to probabilistic automata, the mapping becomes different because you have both min and max nodes in that particular setting. So the algorithm becomes different in a sense as well.
But the complexity remains the same?
No, the complexity is harder. I mean, so for labeled Markov chains, we can compute in polynomial time, and for probabilistic automata, we've shown that it's in PPAT, but we haven't shown that it's polynomial. I doubt it is. So.
Maybe one more?
I can actually say something about your question. So this metric in particular, the one that Franck presented, goes well with the statistic model checking. So if you can, in a statistical model checking, you answer a question probabilistically within a given confidence, then you can use this distance to then infer within another, of course, lower confidence, the same probability for another close enough. So that, and also from here you can define the concept of robustness.
All right. Thank you. So we're breaking now for lunch, and I believe